Welcome back to AI Paper Podcasts. For years, this idea of truly autonomous data science, it's felt a bit like chasing a myth, right?
Absolutely. We've had models that can generate code, sure, but getting them to think strategically, to actually manage a whole complex workflow from end to end, that's been the real hurdle.
Exactly. They just lack that high-level orchestration. But this week, we think we found a paper that really makes a dent in that problem. And interestingly, it's coming from an open-source 8 billion parameter model.
Yeah, we're diving into DeepAnalyze, Agentic large language models for autonomous data science. And it's exciting because it directly targets that core weakness in existing LLM agents, the lack of strategic coordination, and importantly, adaptive optimization for messy real-world data tasks.
Okay, perfect. So before we get into the leads, let's do our quick 60-second summary for everyone. Why is DeepAnalyze such a big deal?
Right. So the problem it tackles is that older LLM agents, they were often stuck in rigid, predefined workflows. They couldn't really adapt or orchestrate multiple steps effectively based on, what was actually happening in the environment.
They lack that flexibility.
Exactly.
Yeah.
And the solution here isn't just throwing more parameters at it. It's this really clever curriculum-based agentic training method. The key idea is to train the model progressively, almost like a human apprentice data scientist. First mastering individual skills, then learning to combine them for complex tasks.
Mimicking the human learning curve. Makes sense. The impact.
Well, the impact is pretty immediate. This 8B open model, DeepAnalyze, it actually achieves state-of-the-art results. It's outperforming some of the big proprietary models like GPT-4o and Claude variants on key benchmarks.
Oh.
Especially, and this is key, on tasks that need long-chain reasoning and generating proper analyst-quality reports, the open-ended research stuff. So it definitely shakes things up for autonomous data automation.
Okay, that's a fantastic summary. So let's unpack that. You mentioned moving from brittle workflows to an adaptive agent. That sounds like it hinges on how the model interacts with its environment. This need for what the paper calls autonomous orchestration and adaptive optimization. How do they actually build that interaction pattern?
Yeah, that's central. They basically standardize the model's thought process using a set of 5 specific actions represented by special tokens. The model itself autonomously chooses which action to use next. Think of it like giving the LLM a structured way to decide its next move instead of relying on rigid manual prompts.
Okay, 5 actions. Can you walk us through them? What's in this decision loop?
Sure. It follows a logical flow, kind of like a human analyst's workflow. First, there's analyze. This is the planner. It handles the high-level reasoning, reflection, checking its own work.
The strategic brain.
Right. Then, critically, there's understand. This one's specifically for interpreting data sources, figuring out database schemas, understanding the columns in a table it just got back, or even processing text from a document.
Okay, so analyze plans, understand, interprets the actual data structures. Got it.
Exactly. After that, you have the tools for doing the work. Code is for generating the necessary Python code using things like pandas, SQL, matplotlib, you name it.
Standard data science toolkit.
Precisely. And then execute runs that code and, crucially, gathers feedback from the environment. Did it work? Did it throw an error? What data came back?
Closing the loop with the environment.
Yes. And finally, answer is used to produce the final output, whether that's a specific result or a full research report. And the really neat part is that the model decides the sequence entirely on its own. It figures out, okay, I need to analyze now, or, let me understand the results of that code first, or, right, I'm ready to write the answer.
That really highlights why older agents felt so rigid. They lacked that dynamic decision-making. The paper mentioned an ablation study too, right? Something about removing one of these actions.
Yeah, they specifically tested removing the understand action, and the results were pretty stark. Performance on complex benchmarks, like BabStep, dropped significantly. It confirms that just seeing the raw output of code isn't enough. The agent needs that dedicated step to deliberately process and make sense of the data structure before it can plan its next move effectively. It's like the difference between just glancing at a spreadsheet versus actually reading the column headers and understanding the relationships.
Okay, so the architecture is elegant. But let's talk training. Autonomous data science, especially complex tasks, suffers from reward sparsity, right? If you need 10 steps to work perfectly, getting that final reward is tough for standard RL.
That's a huge challenge. Conventional RL really struggles when you need multiple integrated abilities to succeed only at the very end.
So the paper claims this agent learns more like a human using that curriculum approach. How do they condense that learning process and, crucially, get enough good training data? Humans take years.
Right. That's where the curriculum-based agentic training comes in. It's designed specifically to tackle that reward sparsity by building up complexity in stages, much like training an apprentice.
Okay, break down stage 1 for us. Laying the groundwork.
Stage 1 is single ability fine-tuning. Think of this as the foundational skills phase. They used around 470,000 data samples here, focusing intensely on the basics. Solid reasoning, understanding structured data, powering that understand token, and becoming really good at generating data science code.
And did it work? Any metrics on that?
Oh yeah. The impact was substantial. The base model they started with scored about 30.4% on the DS1000 code generation benchmark. After just this first stage of fine-tuning, DeepAnalyze jumped to 54.8%.
Wow, okay. That's a big leap just on foundational scale.
It really locks in that core competence.
So stage 2 must be where the magic of orchestration happens, knitting those skills together.
Exactly. Stage 2 is multi-ability agentic training. This is more like the on-the-job training phase. They use reinforcement learning here, but in interactive environments, using about 35,000 trajectory samples. The model has to use its different skills together now. It has to plan sequences, execute code, deal with errors, process the feedback, and iterate. This is where it learns to actually orchestrate and optimize in dynamic, messy situations.
And they mentioned synthesizing training data, data-grounded trajectory synthesis, and something called keyword-guided reasoning trajectory synthesis. How does that help ensure the model focuses on the data structure?
That's about improving the quality of the training data for that RL stage. They basically inject specific guiding phrases into the synthetic reasoning paths prompts, like, let's examine the table structure more closely, or I should verify the column types before calculating this.
Forcing it to articulate those checks.
Precisely. By making the model say those steps internally during training, they enforce a better grounding in the actual data structure within its reasoning process. This helps it handle real-world data inconsistencies much better later on.
Okay, the training methodology sounds really solid. But the proof is in the pudding, as they say.
Yeah.
How did DeepAnalyze actually perform against the models we use, like every day, the GPTs and Claudes?
Well, this is where it gets really interesting. It achieves state-of-the-art results across several key benchmarks. On Data Asset Bench, which tests the whole pipeline prep, analysis, modeling, viz insights, it showed really strong end-to-end performance.
Okay, good baseline. But what about specific skills?
Get this. On DS1000, the code generation benchmark focusing on pandas, NumPy, Matplotlib, DeepAnalyze 8b scored 61.7% overall accuracy. That actually surpassed GPT-4 Turbo, which came in at 53.9%.
Wait, an 8 billion parameter open model beat GPT-4 Turbo on a standard data science coding benchmark.
Yep. That's kind of a big deal. It really shows the power of specialized training for this domain.
Definitely raises eyebrows. But you mentioned earlier its real strength might be in more open-ended research tasks, like that DAB-step research benchmark, where pure orchestration is key.
Absolutely. That's where the curriculum training really shines. DAB-step research tasks involve generating a full research report with very little step-by-step guidance. What they found was proprietary API-based agents, like GPT-4o, tended to struggle when they didn't have that explicit handholding. Their performance dropped off.
They couldn't autonomously orchestrate as well.
Exactly. DeepAnalyze, having been trained specifically for that kind of interactive multi-step problem solving, consistently outperformed them on these open-ended tasks. It's better at self-correction and adaptive planning when faced with ambiguity.
And it wasn't just about getting the numbers right. The quality of the output mattered too.
That's a crucial point. The reward signal during the RL training wasn't just did it get the right answer. It explicitly included metrics for report quality. Things like usefulness, richness of analysis, soundness, interpretability, and even readability.
So it's trained to produce something a human analyst would actually find useful.
Right. It aims for structured, insightful reports that genuinely resemble analyst-grade work, not just code snippets or isolated figures. That's critical if you actually want to use this in a business setting.
Okay, let's make this concrete. The paper included a case study, right? Something about payment processing fees, notoriously complex.
Oh, yeah. A perfect example of real-world messiness. The agent had to analyze 1,000 different fee rules. These rules spanned 769 different merchant category codes, or MCCs,
Always tricky.
4 different card schemes, and 6 different authorization characteristics. It had to ingest policy documents, structured transaction data, and figure out how it all connected.
And the rules themselves, how complex are we talking?
The paper calculated a complexity metric. On average, a single fee rule depended on 8.72 different parameters.
Wow. Almost 9 factors just to determine one fee.
Yeah. Some rules involved up to 15 distinct characteristics. It really highlights why automating this kind of analysis is so valuable. Doing it manually is just incredibly time-consuming and error-prone.
So did the agent manage to untangle it? What were the key findings?
It did. It successfully extracted the core fee calculation formula. Fee fixed amount plus rate transaction value 10,000. It even calculated the average fee for a €100 transaction, 1.42, and identified the typical ranges for fixed amounts and rates.
Okay, so it got the basics, but did it find deeper insights?
Yes, and this is where the data science aspect comes in. It uncovered strong correlations between parameters that effectively define hidden pricing segments. For instance, a very high correlation between the account type and whether it was a credit transaction.
Things a human might miss just looking at the rules individually.
Potentially, yeah.
Yeah.
Also, strong links between card scheme and account type and card scheme and credit transactions. It points to underlying structural logic in the pricing that the agent could identify through systematic analysis.
And what are the practical takeaways from that? For the payment processors or the merchants?
Well, for the processors, that high complexity metric, nearly 9 parameters per rule, is a red flag. It suggests a clear opportunity to simplify and consolidate their rules, potentially making their system easier to manage without necessarily hurting revenue.
Makes sense. And for merchants?
For merchants, the analysis points towards optimization strategies. Things like consolidating transaction volume to potentially get better rates. But maybe most interestingly, the analysis apparently showed a direct, data-backed link between fraud levels and pricing tiers.
Ah, so managing fraud better could directly lower your processing costs.
Exactly. It provides a clear, data-driven incentive for merchants to invest in better fraud management systems. That's a tangible business insight derived autonomously by the agent.
What really impresses me here is the full scope. It sounds like the agent went from handling messy input data like potentially missing MCC codes or validating country details all the way through complex analysis to delivering strategic business recommendations in a polished report.
That's the key takeaway. DeepAnalyze really does seem to move the needle on autonomous data science. That curriculum-based agentic training allows it to achieve that adaptive orchestration, handling the whole process where older agents might have needed manual intervention or followed brittle scripts.
So we're looking at an 8 billion parameter open model capable of producing analyst-grade reports on complex, messy, real-world data. The implications, especially for operational AI in finance or other data-heavy fields, seem pretty significant.
Absolutely. And the paper itself hints at future directions, like integrating these kinds of analytical insights directly into real-time systems. Think AI-driven authorization decisions or dynamic fraud prevention based on this deeper understanding.
Which leads to a fascinating thought for you, our listeners, especially those of you working in AI research or ML engineering.
Yeah, the question is, what complex multi-stage data analysis task, something that currently takes maybe weeks of human effort in your field, whether it's finance, bioinformatics, pharma R&D, whatever, what will be the first such task to be fully and reliably automated by these more strategic agentic LLMs like DeepAnalyze?
Something to definitely chew on. Thanks for joining us for this exploration of DeepAnalyze.